Okay, the next speaker is Brooks Paige, who's going to talk about semi-interpretable probabilistic models.
Okay, great. Hi. So hopefully this is a great counter or companion talk, I guess, to Dustin's talk. So here is one kind of interpretable model that we're all familiar with, linear regression. So it's great, right? We predict the target variable from some hand-designed or hand-selected features, and the estimated parameters themselves are directly interpretable as well as marginal effects. To what extent does a change in some value of a feature x affect our target y? Here's a less interpretable model that we're also probably all familiar with. Here we've traded the simple linear function for some complicated nonlinear function, maybe with interactions, maybe a neural network. Now we're no longer able to make sense of our parameters, but this often might have better predictive performance. Let's do this again. Here's another example of a classic statistical model. Here's a Bayes net. So this is a medical diagnostics example. Someone shows up in the hospital with shortness of breath, and we want to know if they might have tuberculosis. This is a generative model with latent variables, which means we can do things like query whether there's been recent travel abroad, or order more tests like an X-ray, and then revise our estimate of whether or not they do have tuberculosis. So this model has interpretability baked in by design. Random variable nodes have clear sort of semantics. Edges represent causal relationships in the real world. Conditional distributions are easy to hand specify or learn from data, like incidence of bronchitis in smokers or non-smokers, for example. But like, say you want to do the same kind of thing of this, but for data which are images of handwritten digits. Now, in the last model, everything was binary data. It's a simple property outcome of a test. Here, our data is pixels in an image. So we immediately have questions like, how do you specify the probability of an image? What are the latent variables? What sort of would this generative process be? And so one approach is we just throw up our hands, and instead of specifying a model at all, we just go and try to learn it from data. And so here's kind of a very common approach. So this is a variational autoencoder approach. And so we say, all right, we're going to have a graphical model where the conditional distribution is parameterized by the output of a neural network. And we're just going to say there's two kinds of nodes. There's our data, this image that we might observe, I'll call it X, and a vague Gaussian prior over a latent. And the latent is just going to be everything we don't know that might cause it. So we can still fit this model using variational inference to estimate an approximate posterior, and we can learn the parameters of this conditional distribution on the right. We do this from sampling from an encoder or a guide program, and use this to compute stochastic gradients of an evidence lower bound. But I won't talk about how you fit these. I think there's an inference section in the afternoon. But even if this is a good generative model in the sense that it assigns high probability to our data, we can't really use it in the same way as the medical diagnostic model. So like, what is this latent variable? It has no clear semantics, even if we can use our Z to generate this latent Z to generate an image of a 9. It's just, these are incomprehensible latent variables. So this is often viewed as a hard dichotomy, kind of, between these two types of models. And when I talk to people in other fields outside machine learning, like particularly people in, say, social sciences, there's really a sense of not knowing what to do. So the models on the left are great. They can be used to like pose all sorts of questions. People understand when they're working, when they fail. But other times, maybe what's really important is getting predictive performance right. Or maybe we just don't have any idea how to write a likelihood for some types of data. And so people coming from the left maybe then find themselves either skeptical of machine learning or wanting to use it but not knowing how to convince their like bosses or friends or peer reviewers. And like mainly on the other side though, if you're using models on the right, then it's hard to sort of imagine like restricting yourself to models where you have to write the whole thing down from scratch. So my main point here is that I think there is kind of a middle ground that exists between these statistical models and these machine learning models. And I think the deep probabilistic programming languages and libraries that we have today actually make it pretty easy. So I'm going to run through a few examples. I'm going to start with these same famous handwritten digits. So here we actually do have some data. There's labels that go along with every one of these digits saying which number is it. So this digit, certainly, we have something interpretable we can use. So let's pull that out and explicitly make it part of our generative model. And everything else, we're just going to call nuisance variables. And these are whatever the uninterpretable latent variables might be that they capture any other unexplained variation in the data. We're not going to request too much of them from now, but this gives us a generative model which kind of looks like the one we had a moment ago, but instead of saying, okay, we have this graphical model where there's our latent Z that captures everything and then it just produces X through a neural network, we're going to say, well, we have a label Y, that's something that is interpretable, and we'll use that to generate it alongside this uninterpretable bit. And so now we still have a likelihood here that generates X. This is still parameterized by a neural network, but it's a model that kind of makes sense. And so this, the details, I guess, you can fit this still by maximizing an elbow. So there's a semi-supervised learning paper from Kingma et al., which deals with this for this particular model. But I'm less interested in kind of, so that was in a semi-supervised learning setting, and I'm less interested in sort of learning digit classifiers than in how we can use this approach to learn novel sorts of generative models. So here, it turns out this does work. So you can say pick a single digit and then move around this nuisance variable. And as it turns out for handwritten digits, the nuisance variable mostly captures some aspects of handwriting style. So we can do fun things like this. So that was a fairly unambitious graphical model. So can we try to generalize this to arbitrary and more complex model structures? So here's kind of the setting, right? We had this interpretable factor, observed data, and this kind of nuisance variable. So let's try moving from one digit to many digits. And this is going to then also take advantage of compositional properties of graphical models in sort of the traditional sense. So instead of looking at this canvas with 1, we're going to look at these will have anywhere from 1 to 3 digits placed on them somewhere in different sizes. And to make a generative model for this kind of data, we actually just take the old generative model for the single image and add a couple other random variable nodes. So we add something which samples a count. How many digits are there? K, 1, 2, or 3. And we sample some parameters of basically an affine or a linear transformation that projects, are we going to shrink, scale, or translate this one image onto somewhere else? And so now we're literally describing the generative process of how to make this new data, the X in the bottom right, in a way where the only part of it that was not interpretable, the only bit that's the magic neural network, is that one little conditional distribution that we actually already fit already for generating a single digit given its label and this nuisance style parameter. The rest of this is fully interpretable. And we can do inference kind of in the same way that we were looking at inference a moment ago. So we can learn an approximate posterior over these new variables, these transformations A, which scale and rotate or translate, and the count variables given this combined image. And then once the combined image is split into individual digits, we can identify the label and the style, these old Zs and Ys, kind of the same way as before, using even the exact same inference that we used. We don't have to retrain anything. So these are really building blocks here that we can put together in a graphical model, like the way we're used to putting things together in graphical models. So we can run this new inference network, and it can say, look at one of these images and tell us how it can count how many digits are in this image. How you can localize, right? So invert this affine transformation that projected this down. And this kind of looks like the sort of inference that we were doing in graphical models before. But now sort of our approach is this kind of amortized inference, stochastic variational inference approach, as opposed to before. And it's possible to construct an estimator for this, and it took a bit of work for this particular example for us to do it, but it's actually, you can now go and just implement this model in languages like ProbTorch or Pyro, and it will construct an estimator for an elbow for you, and you run gradient descent on the parameters. So this is great, right? So now we've kind of found something which really fits in this middle ground. And I think there's a lot to be found by sort of looking at statistical models and thinking, where can we use deep learning in a very small part of this in order to incorporate data that we have or things that we might know, but where we couldn't otherwise fully specify the model. So that was a graphical model, and here's a linear regression example. So here, linear models for house prices. So say you have a whole bunch of house price attributes. I'm sorry that turned out blurry, but things like location accessibility, neighborhood amenities, structural features like square footage, building age, number of bedrooms. And so when you predict house prices, On the one hand, maybe you're trying to build a model to predict house prices. Maybe you're a realtor and you're pricing houses. But a lot of people are using these not actually because they care about the house price, but because they care about revealed preferences. So they want to ask questions like, how much do people in a particular area buying houses value being close to a park, being close to transit, having an extra bedroom, et cetera. And they do this by looking literally at the regression coefficients and estimating consumer willingness to pay. So the neural network will make better predictions, but people aren't necessarily using it in the same way. So what is this model missing? Well, the linear model that looks on the left is leaving a lot of explained variance on the table. And on the right, we have things like street view images. On the right half of the slide, and these aren't things that you're really used to incorporating in a linear regression model. But there's a lot here. So we were hoping mostly to capture things like visual desirability of an area, but actually if you look at these photos, so these are from Google Street View and Bing Maps, there's a lot of things about land use and so on. And I should mention we're looking at a data set from a large mortgage lender in the London area. And so we can fit this with a two-stage sort of estimation process. And at the moment, we don't use any automated inference because we're worried about confounding. But here's basically the idea. And this will work, I think, for anything like this. But you fit a machine learning model to predict from only the housing attributes. Then you fit a new one to predict the residuals from these images alone. And then you throw out the first model. And so now you say, OK, well, using that second model, I have something that uses machine learning on these images to tell me a thing that has to do with these house prices that I can't get from using these attributes that I care about. And so if I then go and look at this, this is an additional factor that I can use to control for variation in house prices that I can see in these pictures but aren't due to my factors. And then you can go and refit linear regression, do something like look at these marginal effects. And we saw kind of entertaining changes, like things where when you don't control for visual desirability, then it looks like people prefer older buildings. But once you control for what things look like, actually the newer ones are quite good. It's just a lot of the new ones are ugly. We can also do fun things like plot a map that shows this scalar value for every street in London and look at places like where is surprisingly pretty, where is surprisingly ugly. Or this kind of shows what happens if you pick up a building and drop it somewhere else in London, all else being equal, including like size, et cetera. And so you see things, if you're familiar with parts of London, then a few of these are amusing or unsurprising. Okay, I'm going to spend the last 1 minute giving one other example at a very high level. So we were looking at modeling chemical reactions. And this is a problem that's recently kind of started getting interest from the machine learning community because there's a large public data set now available. And classical methods will say, look at these reactants on the left, produce some kind of templates that say, okay, well, here's parts of a molecule that we know combine with each other in certain ways and predict outputs. Machine learning methods do something kind of the opposite, which is you take these reactants, you represent them as a graph or a text string, and then you train a neural network which outputs a graph or a text string on the right and says these are the products. So these both have benefits, but we cheated. So we went and talked to a chemist and asked, well, how do you actually think about these reactions if you're trying to do this, say, in a university level class? And so one way of characterizing a reaction is by this sort of stepwise movement of electrons, these arrow pushing diagrams. And a large majority of organic chemistry reactions that are even in this data set can be described by linear electron flow, where you say, break a bond, form a bond, break a new bond, form a bond. And this alternating path eventually terminates when the reaction stops. And you can actually then formulate this basically as a Markov model where you say, okay, we're going to go predict the mechanism by which this reaction occurs. So we're going to follow the electrons. This bond between the lithium and this ring here breaks. This then goes and adds on to the right. This other bond to the oxygen breaks, and so on. And you get out of that for free the products. So if you can predict the mechanism, then you predict the products. And we formulate this effectively as a Markov model where the transitions are parameterized by a big graph neural network. And so that part's complicated, but the sort of representation level is not just input to products, but rather input to something that is at least auditable, and then to products. So this has kind of state-of-the-art performance at the time we ran it, but that's actually the boring part. It's a few % better on these problems, but really the interesting thing is it gives you estimates that actually show kind of an understanding of chemistry. So we threw it a bunch of problems from an organic chemistry textbook and that were really out of scope for the kind of things that show up in a patent database, which is where the data set comes from, and it consistently shows, I think it understands chemistry better than me. I've picked this up from the chemists. And it also makes mistakes that look human, right? So the first strike here is wrong, but somebody who is informed in the area looks at it and it's like, oh, I see, that's like a reasonable mistake. And the second choice here is actually the correct one. And so this provides a high-level explanation of why the system predicted what it did, but not in sort of a post hoc explain what I did way, but rather in a here's actually the process that I'm predicting. So by just sort of changing the modeling layer to something which is a simple Markov model that we understand well and using deep learning to parameterize this confusing transition function of how does an electron flow, then we have something which is a middle ground between just end-to-end deep learning and template-based systems. So my main idea here that I guess I would try to get across is this isn't super hard. Like, you can do this. So if you have some domain knowledge and you have kind of an idea of here's a model that should work, and you have an idea of here's some data that I don't know how to use, classical statistical models are great, right? They're interpretable by design, and deep learning is pretty good at fitting functions and at conditional density estimation. And so if you kind of use these to their strengths, then you end up, I think, able to build new kinds of models that actually are really useful across sciences. So thank you to my many collaborators who are on these projects.
Time for a couple of questions. It's really hard to see with the light. Yes, Riff.
Great talk. In general, I love this direction. But one thing that keeps coming up that is really visible in the 3 digits model is that you're ultimately kind of deeply reliant on this notion of sort of independent compositionality at the level of the image generation, digit generation itself. So you have this system where you can generate the digits independently and then just sort of independently composite them together into the image, and that's why the whole thing works. That's why you're able to kind of ignore the dependencies between them. Can you say anything about that, or like whether that's a big problem for you, or how you view that? Or?
Yeah, so the question, the question is, here for the digit example, we really, it worked because we were able to leverage the fact that the digits are combined after being generated independently, sort of post hoc, and you can factorize it in this way. Yeah, I think that's true. That does help there. And so obviously this is a toy example, so multi-MNIST is not a real world data set. But I think I think the parallel holds at least weakly for a lot of real data that we look at, where you'll have objects in a scene and a lot of the objects may be different but can be considered independently and then are composed into a greater scene or so on. So it's true, but I think often like we can identify places where this kind of independence does exist and then leverage it.
Do you have any examples where this doesn't work, this approach doesn't work? Maybe the understandable part doesn't give you any information, or how would this fail?
Yeah, that's an interesting question. So it could definitely.
Could you repeat the question?
Sorry. The question is, how would this fail? So is there places where this doesn't work, and sort of what are the failure modes? I think failure modes. So an easy failure mode that can happen if you're not careful is if you're, especially in the first case, if you're looking at deep generative models that have a sort of nuisance variable that tries to capture unexplained variation and other factors that you understand that you want to use to be able to control the generation and use for inference. If you aren't a little bit careful in this, you can end up ignoring the factors you care about entirely. So in the limit, you could imagine a case where if you had trained a variational autoencoder that could reconstruct MNIST perfectly, and then you add in a little bit of side information about the label, then if you're kind of at a fixed point in the optimization where looking at the label isn't going to help you with your reconstruction, and this kind of objective function is typically based on reconstruction. So I think in some of these cases, it requires careful thought about how to structure the objective function, maybe slightly differently from the standard VAE setting, if
Thank
that
you.
answers.
Okay, thank you very much.